Geometry of Knowledge on episode 42? Seriously?
Yep, that's the request we got. Let's start.
Okay, let's unpack this. Welcome back to the deep dive. Today, we are undertaking a mission that feels, well, a bit different. It's less about what we are looking at and more about the optical quality of the glass we're looking through, if that makes sense.
It makes perfect sense.
Yeah.
We are studying the ultimate instrument of observation, you could say, the computational lens.
Right.
And our sources today, they argue that this lens, it's not just a transparent window onto mathematical reality.
Okay.
It's actually a fundamental source of curvature and refraction. It bends things.
Right. So for centuries, classical analysis, it treated mathematical truth, especially things like infinite processes.
Like series convergence.
Exactly. Does an infinite sum converge to a finite limit, a lot of laws, or does it just shoot off to infinity?
Yeah.
It was always presented as this simple, elegant, binary choice.
Pure Platonic certainty. Either it does or it doesn't.
Yeah.
But the reality our framework explores, and this is really the core thesis of this deep dive today, is that computation, which is, let's face it, the only instrument we actually have to probe that certainty.
Right. The only way we can actually calculate anything.
It fundamentally warps the results we see. Now, it doesn't destroy the underlying truth,
Okay, that's important.
but it transforms that simple binary diverges into this rich, complex spectrum of knowability. What can we actually know?
And here's where it gets really interesting for you, the listener. This framework, this thing we're calling computational lensing, it doesn't just apply to some obscure mathematical series nobody's heard of.
No, not at all.
It actually unifies everything we've explored in previous deep dives. We're talking about the constraints we saw on the prime walk,
Yeah, the slow drift.
the speed limits of logic itself, even the weird geometry near event horizons.
They're all visible effects, different facets, you could say, of this single computational lens distorting our view.
Wow. Okay.
The lens acts because, while mathematical truths might exist out there in some ideal Platonic realm, what we can know about them, what we can access, depends entirely on the tools we use. Formal systems, algorithms, Turing machines that have limits.
Bounded machines, real machines.
Exactly. And this limitation, this boundedness, introduces three primary predictable effects into how we observe things: magnification, distortion, and occlusion.
Magnification, distortion, occlusion. Okay, so let's start by maybe establishing the baseline. What's the view before the lens?
Good idea. Let's set the stage. We begin in what the sources kind of poetically call the classical paradise. This is the view through the naked eye, metaphorically speaking.
The world of pure math.
Pure mathematical analysis, yeah. It operates under these like ideal assumptions: infinite time, perfect information, unlimited precision, no constraints.
And in that world, the decision tree is clean. A series either stops nicely at some limit or just goes to infinity. Simple.
And this clarity, it isn't accidental.
Yeah.
It's built on some really solid foundational concept.
Yeah.
Take the Cauchy sequence, for instance. This concept is brilliant because it gives you clarity without needing to know the final answer in advance.
How does that work?
It just says, look at the terms of the sequence. As you go further and further out, do they start huddling together, getting arbitrarily close to each other?
Ah, okay. Not necessarily close to the final limit, but close to one another.
Exactly. If they do that, they're convergent. We know they are approaching some definite limit, even if we haven't calculated it yet.
It's seeing a group of marathon runners way off in the distance. You can't see the finish line. But if you notice that after, say, 25 miles, all the runners are staying within 5 feet of each other, they must all be heading toward a single, common, finite point. They're going somewhere specific.
Precisely. It's a fantastic analogy. And that limit in classical math is guaranteed to be unique and to exist. Why? Because we assume the real number line is what's called a Hausdorff space, and that it's complete.
Okay, Hausdorff space. That sounds technical. Why does that matter for convergence?
It's maybe a bit technical, yeah, but the implication is really powerful. A Hausdorff space basically guarantees that any two distinct points are truly separate. You can always find little neighborhoods around them that don't overlap.
So points have personal space.
Huh. Yeah, you could put it that way. They have personal space.
Yeah.
And why that matters for convergence is it guarantees unambiguity. If a sequence converges, it can only converge to one unique limit point.
Ah, okay. You couldn't have a sequence that's somehow heading towards both 3 and 5 at the same time.
Not in a Hausdorff space, no.
Yeah.
That would be like our marathon runners simultaneously finishing in two different locations. Doesn't happen. So the classical paradise is this perfect map where every destination is sharp, singular, unambiguous.
Okay. Crystal clear. But now, we introduced the lens, the computational lens,
Right. And this lens, it's not made of glass. It's made of logic.
the rules of the game.
Yeah, the formal framework of computability theory. Think Turing machines, think axiom systems like Zermelo-Fraenkel set theory. That's the material of the lens.
And you're saying this lens is far from transparent.
Oh, it's incredibly dense, and it has this enormous gravitational field. The massive objects creating the warping effect are those fundamental, inescapable limits we keep bumping up against in logic and computation.
The big ones. We're talking the halting problem.
Yep.
Gödel's incompleteness theorems,
Uh-huh.
and those crazy uncomputable functions like the busy beaver.
Exactly. And the crucial point is, these aren't just temporary technical hurdles we haven't figured out yet.
They're fundamental, like speed limits.
Permanent cosmic speed limits for
Yep.
logic, yeah. And these limits, acting as the mass in our lens, they transform that simple binary classification converges or diverges into this complex, nuanced spectrum, a spectrum of knowability.
Knowability.
Not just truth, precisely. They force us to recognize a kind of hierarchy of knowledge that classical, pure Platonic mathematics often just ignores because it only lives at the top layer.
Okay, this hierarchy feels important. Let's lay it out.
It's absolutely vital for everything that follows. So at the top, you have truth, the ideal Platonic fact. Does the limit exist? Yes or no?
Okay, layer one.
Then, below that, you have proof. What can we actually demonstrate is true within a finite logical system, like ZFC? Can we formally prove that doll exists?
Layer two.
Yeah.
Still fairly abstract.
Right. And then finally, the layer where the lens really operates, computation. What can be calculated by a physical bounded machine, a real computer, even an idealized one like a Turing machine? Can we actually find the digits of
Truth, proof, computation.
Got it. In the computational lens, it primarily acts on that third layer, computation. But its inherent limits, finite time, finite memory, finite energy, they feed back upwards, they affect how we perceive proof and even truth. The lens determines not just what's true, but what truth is accessible to us.
Accessible truth, that's the key idea. All right, let's dive into the first effect of this lens, magnification. You said this takes that crude classical binary label, converges, and breaks it down.
Exactly. It resolves it into more detailed subcategories. It's not just if the limit exists, but how fast you approach it, and crucially, whether the limit itself is something we can actually compute.
So looking through the lens splits convergence into different types.
That's right. We get trivial convergence, maybe straightforward is a better word. That's where the limit is a computable real number, something like pi or e or the square root of 2. We have algorithms to calculate their digits.
Okay, the easy cases.
And then we get this much stranger phenomenon, which the sources call quasi-convergence. They describe it as being like chromatic aberration in a physical lens.
Chromatic aberration. That's when a lens can't focus all colors at the same point. It creates fringes, a blur.
Exactly, a permanent blur. So the series converges classically. The limit definitely exists. It's a specific point out there in the Platonic realm. But when viewed through the computational lens, Lawler turns out to be an uncomputable real number.
Uncomputable, meaning no algorithm can actually calculate its digits.
Correct. The lens tries to focus, but it just can't resolve the digits. Why? Because any algorithm that would define Lioradal to calculate it turns out to rely on solving one of those fundamental undecidable problems, like the halting problem.
So the truth is out there, like the X-Files, but our instruments, our computers, can never actually tune in the signal. It's like a mathematical mirage in the desert.
That's a great way to put it, a mirage. And the perfect example is this thing called the Busy Beaver Zeta series. Looks complicated, say, to the Zeta, where primes.
Okay, BBN, the busy beaver function, that's the one that calculates the maximum number of ones an end-state Turing machine can write on a blank tape before it finally halts.
Yeah, exactly. And $27 is just some fixed, absolutely enormous integer. We don't know what it is, but it's a specific number.
So even though the series looks scary because $27 is just a fixed, albeit huge number, the terms in that sum, high raised to the power of minus that huge number, they get incredibly small, incredibly fast.
Plummet exponentially fast, yeah. So classically, this series is absolutely, definitely convergent, no question.
You can prove it converges in ZFC, our standard math framework.
Easily provable. But here's the paradox the computational lens introduces. The actual value of the limit, Lawler, the number this series sums to, is uncomputable.
Why? Just because BB27 is huge?
Not just because it's huge, because to actually calculate the sum, you would first need to know the precise value of BB27.
And we can't compute that.
We've proven that calculating baby 10 for arbitrary, especially for large ones like 27, is an uncomputable problem. It's directly equivalent in difficulty to the halting problem.
Wait, I need to stop you there because this feels subtle but really crucial. BB27s is a specific finite integer. It exists. Why can't we just say, okay, it's large, maybe we don't know it, but it exists, therefore the value of the series must also exist. Isn't that enough?
The value exists mathematically, yes. In the Platonic realm, it's a fixed point. But the computational lens has a stricter requirement. It demands an algorithm to produce the digits of that value.
Ah, it's about the process, not just the existence.
Exactly. If the only way to define the algorithm that produces look fundamentally requires you to solve an uncomputable problem first, like finding $27, then the digits are computationally inaccessible. Right. Forever. You cannot build a machine, even in principle, using standard computation. That will calculate that limit exactly.
Wow.
It's a truth that is provable in ZOC, but its value is fundamentally measurably lost to computation. That's quasi-convergence. The lens shows us a blur where classical math saw a sharp point.
That's a powerful and frankly slightly terrifying distinction. Existence versus knowability. Okay.
Now let's flip to the other side. Divergence. Here, magnification reveals something we call quasi-divergence, and the analogy here is gravitational redshift.
Okay, redshift, like light from distant galaxies stretching out, looking redder, appearing slower.
Exactly. So in this scenario, the classical truth is simple. The series diverges. It goes to infinity. It grows forever.
No ambiguity there,
No.
classically.
No. But the lensed view, the computational view, shows us that the rate of divergence is just excruciatingly slow. So slow that, from our finite perspective, the series looks almost stationary. It's hardly moving.
Its escape vector towards infinity is redshifted down to almost zero velocity from our point of view.
Perfectly put. Now, we have to move way beyond the standard example of divergence, the harmonic series, some hundred.
Right. That one diverges, but you can see it move. I remember reading you only need about, 1043 terms to get the sum over 100, which is huge, but...
Conceptually accessible, yeah. It's a number we can write down. But for quasi-divergence, we need to escalate to hyper-slow rates. Think about the triple log series. Sum frag phi nan ln?
Okay, logs slow things down a lot.
They do. Or even worse, imagine a tenfold iterated log series. You apply the logarithm 9 extra times in the denominator.
Wow. Okay, that denominator grows incredibly slowly, meaning the terms shrink incredibly slowly, meaning the sum grows incredibly slowly.
Agonizingly slowly. And what's fascinating here is the contrast between what is decidable and what is feasible.
Ah, this feels like another key distinction.
This is really the crux of what we'll later call practical occlusion. The divergence of these series, the triple log, the tenfold log, is absolutely definable. You can prove it.
How?
Using standard tools from calculus, like the integral test. A mathematician can write down a formal proof, maybe a few pages long, within ZFC, demonstrating rigorously that these sums go to infinity.
So the proof exists. It's knowable in that sense.
Yes. But verifying it computationally, seeing it happen, that's impossibly infeasible.
Oh, how infeasible.
Let's take that tenfold iterated log series. Suppose you just want the sum to exceed a really modest boundary, say $10. Just get bigger than 10.
Okay. How many terms do you need to add up?
The number of terms, the 10, reaches a scale defined by an exponential tower of height 10. So 10 is roughly 10, 10. That's $10 raised to the power of 10 times, starting with 10.
Okay, I can't even comprehend that number. That's way bigger than the number of atoms in the universe, right? Or the age of the universe in Planck times.
Vastly bigger than any physical constant we know. It's just staggeringly large. So large that computing that many terms is physically impossible within any meaningful time frame, like the lifespan of the universe.
So from a finite computational perspective, running on any conceivable computer for any conceivable time, the series hasn't diverged yet. It's like it's in suspended animation.
Exactly. It is guaranteed to diverge eventually, but the eventually is beyond our practical reach, beyond our time. That's quasi-divergence. The lens shows us something effectively static, where classical math saw slow but inevitable motion.
So the lens, through magnification, has really enriched the picture. It's created this detailed spectrum: sharp convergence, computable limit, blurry convergence, quasi-uncomputable limit, rapid divergence, and this agonizingly slow divergence, quasi.
Precisely. And understanding this spectrum, this blurring and stretching caused by the lens, it leads us directly into the second major effect, distortion.
Distortion. Okay, so the lens doesn't just magnify details, it actually bends the picture.
It reveals that the real number line isn't this uniform, smooth, perfectly flat continuum we learned about in school.
It's not. How is it then?
Through the computational lens, it looks more like a warped landscape, a terrain.
A terrain.
Yeah, composed of these easy points.
Yeah.
The computable numbers, think of them as oases in the desert. Points whose digits we can actually generate algorithmically, like pi or e. They're accessible.
Okay, oases. And the rest?
The rest are the hard points, the vast majority, actually the uncomputable numbers. These are like mirages, points like that busy beaver zeta limit we talked about. They exist, but you can't computationally reach them easily, or maybe at all.
I like that analogy, oases and mirages. It gives a kind of geometry to the limits of knowledge, doesn't it?
It does. The computational lens makes us realize that even if a Kachi sequence always converges classically, those runners huddling together, we immediately have to ask the next question. Is the limit they're heading towards an oasis or a mirage? Is it computable or uncomputable?
And the answer determines whether that limit is truly knowable through computation.
Exactly. The lens imposes this kind of local curvature on the number line. Trying to move computationally from a computable point, an oasis, to an uncomputable one, a mirage, is like trying to cross a vast, featureless desert. The distance, in terms of computational effort, might be effectively infinite.
So this warps the whole structure of analysis.
It forces us to always consider that hierarchy we mentioned, truth-proof computation. The computational lens fundamentally introduces geometry into logic itself. Things aren't flat anymore.
Okay, that brings us to the third, and maybe the most dramatic effect. Occlusion. This is where the lens doesn't just blur or distort, it completely blocks the view.
Yeah, this is when the fundamental limits of logic Gödel, Turing, act like a logical event horizon. They turn the blur of distortion into just total blackness. We can't see through it.
A logical event horizon, like a black hole for knowledge.
In a way, yes. Classically, we have the law of the excluded middle. Any meaningful mathematical statement, like series X converges, has to be either true or false. There's no third option.
Yeah.
Full stop.
Black or white.
But the computational lens shows us that. For some cleverly constructed series, the actual classical truth value, true or false, is positioned directly behind the black hole of the halting problem.
So we're not just physically unable to calculate the answer because it takes too long. That was quasi-divergence or practical occlusion.
Right. This is deeper. Here we become informationally disconnected from the classical truth value itself. The truth is provably inaccessible from within our standard logical system, like ZFC.
Provably inaccessible. Wow, how can we construct something like that?
Let's walk through the rigorous construction for an undecidable convergence problem. This is a really powerful example from the source material. We define a series, let's call it sum anon.
Okay.
And the trick is we make the value of each term, anon, depend on the behavior of the Noth Turing machine. Long anoths is in some standard list or enumeration of all possible Turing machines.
So each term is linked to whether a specific program halts or not. This sounds like setting up a logical tripwire.
That's exactly what it is, a logical tripwire. We design a lambda so that it behaves differently depending on what Noether does. For instance, a simple version could be, let $1 equals 102 if the Noether Turing machine, Noether halts within, say, steps. 102 terms converge nicely, remember?
Sum 102 converges.
Okay, but if an Noether running after non-theps, we say 102 equals $1. And we know sum 102, the harmonic series, diverges.
Ah, I see the trap. So what happens to the whole series sum on it all?
Think about it. If infinitely many Turing machines halt, even if they take more than non-steps eventually, this series is going to contain infinitely many terms that look like a non-step or something similar that diverges. It'll essentially contain a tail of the harmonic series.
And if it contains the harmonic series tail, it must diverge.
Correct. But what if only a finite number of Turing machines halt?
Then, after some point, all the null terms will be the 102 type, or something that converges quickly.
Exactly. The series might have a few large-like terms at the beginning from the finitely many machines that halted slowly or ran forever, but eventually it will just be the tail of a series like sum 2022. And that converges.
So the convergence or divergence of the entire series sum hinges entirely on whether infinitely many Turing machines halt or only finitely many do.
Precisely. The convergence status is effectively the halting problem, just rephrased. Deciding whether summing converges or diverges would require us to know the halting behavior of all Turing machines on an nuller.
Which we know is impossible. The halting problem is undecidable.
Exactly. Therefore, we cannot prove within our standard mathematical framework, ZFC, assuming it's consistent, whether this series converges or diverges.
That's the logical event horizon. The classical truth value, it does either converge or diverge in the Platonic realm, is trapped behind the undecidability of the halting problem. We can't reach it with proof. The series is beyond our logic.
And this phenomenon, this logical occlusion, really helps illuminate these three distinct nested locks that constrain our access to knowledge. We often just lump all difficulty together as hard, but the lens forces us to be more precise.
Okay, let's break down these three locks.
The first, the absolute deepest lock, is logical occlusion. This is the barrier imposed by Gödel's incompleteness, the halting problem, undecidable questions. Here, the truth is provably inaccessible. We cannot construct a proof of convergence or divergence, even in principle, like with our undecidable series. It's an improvable truth within the system.
Lock number one, unprovable.
The second lock is practical occlusion. This is the complexity cliff we talked about earlier with quasi-divergence. Here, computation is possible in principle.
Meaning an algorithm exists and it would eventually halt and give the answer.
Yes, the algorithm is finite. But the required time or memory or number of steps just exceeds any physically plausible limit. Think of the hyper-exponential number of terms needed for that 10-fold iterated log series to pass 10. The algorithm would eventually confirm divergence, but the universe's clock runs out first.
Lock number two, provable but infeasible in time or resources.
And the third lock, which often gets overlooked but is becoming increasingly relevant, is economic occlusion. This brings in the energy cost of computation. It links knowledge acquisition directly to thermodynamics.
So computation might be possible within the age of the universe, theoretically.
But the energy required scales so drastically, maybe exponentially, that the cost of finding the truth becomes prohibitive. It's unknowable simply because the price, in joules, is too high.
Like trying to brute force certain kinds of encryption.
Exactly. That's chaos encrypt territory, as the sources call it. Breaking the encryption might be theoretically possible, maybe even practically feasible given enough time. But the sheer energy cost to flip enough bits to run the computation makes the knowledge economically inaccessible. Your energy bill would exceed the GDP of a small country.
Lock number three, feasible in time, but infeasible in energy cost.
Precisely. So knowledge isn't just constrained by abstract logic and cosmic time. It's fundamentally constrained by the energy budget of the observer, by thermodynamics.
Okay, this framework of magnification, distortion, occlusion, and the three locks. It's powerful theoretically, but to make sure it's not just abstract castles in the sky, let's try and ground it. Can we connect it back to a system we've actually looked at before?
Absolutely. And the perfect candidate is the prime walk, which we explored in a previous deep dive. That relatively simple number-theoretic system actually demonstrates all three effects of computational lensing, magnification, occlusion, even distortion, all in one place.
Okay, refresh our memory on the prime walk. You start at some number, and you jump based on prime factors.
You can think of it as moving through states defined by the prime factorization of integers. The key rule was the probability of jumping to a state associated with a prime power. Keydale's is weighted proportionally to 1b-gauls.
So jumps involving small primes like 2 or 3, and their powers are much more likely than jumps involving large primes.
Exactly. And that PAL probability weighting, that is the mechanism of magnification in action right there. It creates a biased view of the state's space. Even though the space of numbers and their prime factorizations is infinite, the heavy weighting towards small primes forces the walk to spend almost all of its observable time clustered around the origin, around numbers divisible only by small primes.
Like it's stuck near the computable oases we talked about earlier.
Precisely. The lens, in this case the WKKO probability rule, magnifies the structure and dynamics near the small numbers. It reveals all this interesting complex cluster behavior near states related to 2 and 3. Things that classical number theory, looking uniformly, might just dismiss as random noise.
Yeah.
The lens shows us detail where we wouldn't expect it.
Okay, that's magnification. What about the other effects? We also saw the walk was incredibly slow, right? It had this weird drift.
Yes. The strained, almost agonizingly slow movement, that double logarithmic crawl or drift we observed.
That sounds familiar.
That is a perfect physical manifestation of practical occlusion.
Like the 10-fold log series.
Exactly like it. The prime walk is known to be ergodic, meaning, theoretically, over infinite time, it will eventually visit every possible state. It will reach states corresponding to arbitrarily large prime powers. The truth of its ergodicity exists, but its double logarithmic drift rate ensures that actually reaching those states associated with large, complex prime factorizations is computationally practically infeasible. It's just too slow to observe within the lifespan of any computer simulation or even perhaps the age of the universe.
So the full expression of its ergodic nature is beyond our time horizon, occluded by practical limits.
Yep. It shows the computational lens isn't just abstract math theory. It describes the actual physical behavior of mathematical systems when we try to observe them over finite time intervals.
Okay, magnification, practical occlusion.
Hmm.
What about distortion or the deeper logical occlusion?
Consider the structure we saw emerging that seemed connected to the Riemann hypothesis. Remember how the walk's initial symmetry seemed to break? But some underlying structure, some residual symmetry, seemed to persist. And that residual symmetry appeared to demand that the important dynamics, maybe related to the zeros of the zeta function, organize themselves along a specific line, the critical line from the Riemann hypothesis.
Right. How does that fit into the lensing framework? Is that distortion or occlusion?
It's a bit of both, perhaps leaning towards how occlusion shapes what remains visible. Think of this. The computational lens, by imposing limits, finite time, the Glommen-PIR bias, acts as a constraint on the system's dynamics. It breaks the perfect underlying symmetry.
Okay.
We only get to see a messy, constrained, broken version of the full dynamics. But the very fact that the remaining structure, the part that isn't completely occluded or averaged out, must still organize itself along that critical line, that demonstrates something profound.
What does it demonstrate?
It shows that the inherent geometry, imposed by the lens, the gauge of the computational field, if you like, constrains the possible shapes of the remaining visible structure. Even where the exact answers, like the precise locations of the zeta zeros, remain hidden or occluded behind complexity barriers, the shape of our ignorance is dictated by the lens.
So the lens doesn't just block knowledge, it dictates the geometry of the remaining patterns, the shape of the shadows.
Exactly. The residual symmetry demanding the critical line is like a residual gauge invariance. The lens warps and occludes, but the underlying laws still force the observable remnants into specific patterns. The critical line is the structure that survives the lensing.
We've used magnification and occlusion to talk about the state of truth, visible, blurry, hidden. Now let's circle back to distortion. You mentioned this connects to physics and even AI. The key idea seems to be non-commutativity.
That's the crucial link. The distortion caused by the computational lens isn't just bending. It implies that computation itself is fundamentally a non-commutative history.
Non-commutative history. Okay, what does that mean in simple terms? Order matter.
Exactly. Order matters.
Right.
In basic arithmetic, A plus B is the same as B plus A. That's commutative, or Billian. Simple, predictable.
Right.
But think about quantum physics. Measuring a particle's position and then its momentum gives you a fundamentally different state of knowledge than measuring its momentum and then its position. The act of measurement changes the system, and the order changes the outcome. That's non-commutative or non-abelian.
Okay, I know that example. How does it apply to computation?
The sources draw a direct parallel. Just like in physics with non-abelian gauge theories where applying transformation A, then transformation B gives a different result than B, then A, the output of a complex computation, or even the outcome or structure of a mathematical proof can depend critically on the order of the steps taken. The path matters.
The path you take to the solution changes the solution itself, or at least the state you end up in.
Precisely. Let's use that fantastic F1 analogy from the sources to make this idea of holonomy clearer.
Okay, F1, I like this already.
Imagine an F1 car racing a lap. The track represents the path, $2 through SpaceTime, or maybe through computational state space.
Got it.
Now, scattered around the track are these special sensors. Let's call them teleporting red signals. When a car passes through one, something happens internally to the car. These signals represent non-abelian gauge fields, like the transformations in the strong nuclear force. Think SU3 rotations. Passing through a signal rotates the car's internal color charge state, let's say.
Okay, so the car has an internal state and the signals change it.
Right. Now, suppose on one lap, the car passes through signal R1 first, then signal R2 later. It completes the lap and ends with a certain final internal color charge state. Call it synonyms.
Nonsense.
But on the next lap, maybe the signals have moved slightly or the car takes a slightly different line. This time it passes through signal R2 first, and then the signal R1. It still completes the lap. It still passed through both signals.
But the final state will be different.
Exactly. The final state, signal final, will generally be different from signal baud because the order of the rotations applied by R1 and R2 was different, and these rotations don't commute. A rotation R1 followed by R2 is not the same transformation as R2 followed by R1.
That difference, that dependence on the path taken around the loop, That's holonomy.
That's holonomy. It's the overall change or rotation accumulated after traversing a closed loop in a space with curvature or non-trivial connections, like a gauge field.
And the huge insight here is the connection. Non-abelian physics is to space what computation is to time.
That's the profound logical bridge the sources propose. Both systems, physical interactions in space, and logical operations unfolding in time can encode history into the final state. Both can be fundamentally non-commutative histories. Our computational lens distorts the geometry of time because the order in which we perform operations, the order we solve subproblems, it matters. It changes where we end up.
Wow. Okay, that connects computation to some deep physics. Now, how does this path-dependent, non-commutative logic play out in artificial intelligence? You mentioned reinforcement learning, RL.
Right. Think about an RL agent. It's trying to learn how to navigate a complex environment, a state space, to maximize some reward.
Like learning to play a game or control a robot.
Exactly. From the perspective of computational lensing, that agent isn't navigating a simple flat grid. It's navigating a fundamentally curved knowledge manifold. A non-Euclidean space where the distance between states and the direction of improvement depends on local constraints, past experiences, the order of learning.
And the reward signal, that's what the agent sees, that's its guide, but you're saying that signal is also affected by the lens.
Absolutely. The reward signal, $3, that the agent receives is almost never the pure, unvarnished ontological truth, $2, about the optimal action.
It's not. What is it then?
It's a projection of truth.
Sometimes it's just structure.
It is structure. The logical event horizon isn't some messy error in the system. It's an elegant, perhaps even beautiful, inescapable feature of any sufficiently powerful, yet finite logical system. It's a boundary condition.
Which brings us back maybe to the biggest philosophical question underlying all of this. If knowledge is so constrained, so lensed, what about the answer to life, the universe, and everything? It can't just be a single number, can it?
No. It seems the answer isn't a fixed number like 42, accessible to anyone who just asks the right question.
So what is it then?
It depends. It depends entirely on your computational lens, the tools, the algorithms, the axioms you're working with.
It depends on your patience with the curvature of time, how long you're willing to wait for those quasi-divergent series to crawl upwards.
It depends on your compute budget. How much energy can you afford to spend chasing down economically occluded truths?
I think. We're moving away from the usual ways we talk about computing theory.
Yeah, we're heading straight into geometry. It might sound a bit unexpected.
It does. Logic, these constraint problems, even cryptographic hardness, it's all fundamentally geometric.
The difficulty isn't just about how long it takes to find a solution.
It's because the landscape of possible solutions is topologically complex, riddled with valleys, ridges, and these sort of hidden holes that block simple paths.
Obstructions baked into the very shape of the problem space.
So these recent breakthroughs in symplectic topology, specifically something called flower geometry,
Quite an advanced area, yeah.
and seeing how this geometry provides a kind of topological certificate, an unchanging mathematical signature for why problems are complex. It basically aims to replace those old computational assumptions.
It translates logic into a landscape, mathematically.
Right.
The core breakthrough is we see hardness as this immutable, measurable feature of the solution space's shape.
So not how long it takes, but what the space looks like.
Exactly. Think of it like this. You count the persistent topological cycles, these holes that don't just collapse away. That count is the certificate of complexity.
Wow.
It suggests if you could map the topology perfectly, you'd know the complexity instantly before a computer even starts running.
So we're ditching the algorithmic stopwatch.
And picking up the surveyor's map, essentially.
Okay, let's start charting this territory then. So to really get this, we first need to make a kind of mental shift, right? A mathematical one.
We do. We have to stop seeing logic just as static rules on paper.
A implies B.
Yeah, abstract rules. And start seeing it as a dynamic, almost physical system.
Okay. How do we begin?
Let's start simply with something called the assignment cube. Imagine you have a logic problem with, say, no variables. 7, 1, 6, 42 dolls, up to 6.
True or false for each one.
Right. Every possible combination of true-false assignments, like true, false, true, corresponds to a corner, a vertex, on a non-dimensional hypercube. Usually we think of it as one-maned.
Okay, so each corner is a potential answer.
A potential answer, exactly. And the edges of this cube, they represent flipping just one variable, moving from one assignment to a neighboring one. That's the basic static search space.
Fine, I can picture that cube, but you said dynamic.
Right, that cube just tells you where you could be, the possible states. It doesn't capture the push and pull from the constraints themselves.
What do you mean push and pull?
If you have a constraint like $6 must be true, and right now you have both $6 and 2 set to false.
That assignment violates the rule.
Exactly. The constraint is basically screaming for a change. It's exerting a kind of force on that state, pushing it towards satisfaction.
Okay, so we need to capture that force.
And to do that, we need dynamics, which means mathematically we need more room. We have to double the dimensions.
From no dimensions to 2 utterers.
Precisely. And this is where it gets really interesting, I think. We step into what's called phase space.
Phase space, like in physics.
Exactly like in physics. We take our dimensional assignment Q, our positions for all stellars, and we pair each position with a corresponding momentum coordinate. We get this 2 other dimensional space called the cotangent bundle.
Okay, cotangent bundle sounds intimidating.
The name isn't crucial. Just think of it as pairing state with force. The coordinates tell us what the assignment is. True, false, true.
And the coordinates.
They tell us how badly we're violating the rules of that assignment. They represent the violation gradients, the forces. Mathematically, they often look like derivatives of some energy function related to the constraints.
Like partial H, partial Putel, potential energy gradient.
You got it. And this whole two-dimensional setup has a special mathematical structure, a symplectic form, which governs how things flow. It's just like classical Hamiltonian mechanics. Systems naturally flow along paths towards zero energy states.
And zero energy means?
A satisfying assignment. All constraints met. No forces acting.
Okay, but hang on. Are these p-ordinates, these forces, just a mathematical abstraction? Or do they actually show up when, a real SAT solver is crunching away?
Oh, they absolutely align. This isn't just ivory tower theory. Look at modern SAT solvers, especially the sophisticated ones using heuristics and branch and bound.
Like deciding which variable to try flipping next.
Exactly.
Yeah.
That decision is often based on some score, some internal metric. That score functions just like our polar coordinate. It represents a calculated force or momentum, indicating how urgent it seems to change that specific variable. We're basically giving that algorithmic intuition a formal geometric basis.
Huh. Interesting.
And more than that, those sharp phase transitions in random SAT problems, where they suddenly go from easy to incredibly hard.
Yeah, the threshold phenomena.
Geometrically, those emerge as symplectic bifurcations. Points in this phase space where the possible flow paths suddenly tangle up exponentially. The geometry predicts the algorithmic cliff.
Okay, so we have this dynamic phase space, $2 dimensions, forces pushing things around. Where do the actual solutions fit into this picture, the assignments that work?
They form a specific structure within this big space, a connected, coherent shape called the constraint Lagrangian. We usually denote it with a fancy math code. It's a smooth submanifold living inside the 2 outer dimensional phase space.
A submanifold, so a surface within the larger space.
Exactly. And it's called Lagrangian for 2 really key geometric reasons. First, its dimension is exactly half of the total space in order dimensions within the 2 null hours, sort of the minimal space needed to hold the solution.
Okay, half the dimension. And the second reason.
This is crucial for our deep dive. The internal symplectic form vanishes on it. Mathematically, 1 omega equals...
What does that mean intuitively? 1 omega.
Think of the symplectic form omega as measuring the inherent twist or flux of the dynamics in the phase space. For this solution manifold MathCo, the fact that the form vanishes internally means MathCo itself is a region of, let's say, pure flat neutrality.
No internal forces.
Once you land on MathCo, there are no internal dynamic forces pushing you along it or off it. The forces and the constraint energy have effectively gone to zero. You've arrived.
So if the solution space itself is neutral, where does the hardness come from?
It comes from how that neutral Lagrangian math call is embedded, how it sits within the surrounding 2-dimensional phase space.
It's about the neighborhood.
Precisely. If the problem is easy, maybe a set of constraints that don't interfere much, the math call sits nicely. It's totally geodesic, which is math speak for flat and smooth, like laying a sheet of paper flat on a table. Easy to navigate.
And if the problem is hard, like those graph coloring problems or finding cliques.
Then the constraints force the embedding to become highly warped. The Lagrangian gets squeezed and twisted, concentrating tremendous curvature into specific regions, these ramified cores.
Ramified core.
These highly curved areas effectively punch symplectic holes through the solution manifold. They create topological twists.
Like knots.
They physically obstruct our ability to smoothly patch together partial solutions. Imagine trying to glue pieces of paper together, but there's a fundamental twist preventing them from lying flat. The amount of this twist is measured by something called Maslov classes. These are topological invariants directly tied to these holes.
Okay, so we've reframed complexity. It's not just time, it's the shape, the curvature, the twists in this constraint Lagrangian math call.
Right. The geometry holds the key.
But how do we actually measure these holes and twists reliably? We need a tool, a diagnostic, that doesn't get thrown off by small changes in the problem, something robust.
And that's where Floer homology comes in. Let's call it HF.
Floer homology. Okay.
Think of it less like mapping a fixed landscape and more like analyzing, say, the complex currents and eddies in a vast multi-dimensional ocean. It tracks the flow.
And this didn't come from computer science originally, did it? This sounds like it has physics written all over it.
You nailed it. It was invented by Andreas Floer back in the 1980s. And his direct inspiration, quantum field theory.
Seriously, like fundamental forces.
Yep. Specifically, he was wrestling with the mathematics of the Yang-Mills equations.
Wow, okay. Yang-Mills describes things like electromagnetism, the nuclear forces,
Right.
and Floer was looking at what exactly?
He was studying something called instantons. These are like they're fleeting solutions in quantum field theory. Think of them as describing transitions between different energy states, like quantum tunneling events.
Okay, so these instantons represent paths between states.
Right. Paths of least action. It's a core principle in physics. Nature tends to be efficient, taking the lowest energy route. Floer basically took that physical intuition and turned it into a rigorous mathematical machine for these infinite dimensional spaces.
Okay, so that's the bridge. And our mission today, then, is to see how this physics-born math, Floer homology, or maybe tools derived from
Here's proxies, yeah.
how it can give us actual numbers, these algebraic invariants, to measure two really different things. One, how fundamentally hard a computational problem is, like for cryptography.
And two, how difficult it is to actually train a huge AI model, like a neural network. Can this geometry predict that?
It sounds almost too good to be true, connecting deep physics to practical AI training.
The core idea we're chasing is that complexity isn't just about how many parts a system has, like variables or parameters. It's about the shape of its possibility space, the topological complexity.
The number of holes or loops in that abstract space.
That's the hunch. That's what makes this exciting.
All right, how does Floer homology actually work? You called it an alchemist's trick, turning continuous flow into discrete numbers.
Yeah, the core idea is to look at a continuous process. Imagine a landscape, a really high-dimensional one, a manifold, and there's a function on it, like a height function. We call this the action functional.
In physics, that's energy or action. In machine learning, that's our loss function, what we want to minimize.
Exactly. And there's a flow on this landscape, like water flowing downhill. It's governed by a mathematical rule, a partial differential equation, or PDE, that essentially says, follow the steepest descent.
Okay, so we have this continuous downhill flow.
FH then zooms in on two crucial things. First, the places where the flow stops, even momentarily. These are the critical points, the peaks, the valleys, and importantly, the saddle points.
Like plateaus or passes in the landscape.
Right. And second, FH looks at the actual paths the flow takes to get between these critical points, the flow lines.
So it's not just the destinations, but the rights connecting them.
And these aren't just any random paths. They're very specific solutions to that PDE we mentioned. In the technical language, they're often called J-holomorphic curves, or strips.
Okay, J-holomorph, that sounds intense.
Yeah.
What does that tell us? Is it just the shortest path, like a straight line?
It's a bit more subtle than just shortest. Think of it this way. The spaces FH usually works in have a special structure. They're often symplectic manifolds.
Symplectic. Okay, why that structure?
Symplectic geometry is basically the geometry of classical mechanics, like Hamiltonian physics, is built-in conservation laws. J-holomorphic curves, in this context, are the paths that naturally follow the structure of the space while minimizing that action functional. They're the true least action paths, the instantons of the system. They represent the most robust connections.
So FH is tracking these really fundamental energy-minimizing connections between the stable points, minima, and unstable points, saddles, maxima.
Exactly. And here's the alchemist's trick. FH doesn't just note these paths exist, it counts them. But it counts them carefully, with mathematical signs like plus or minus 1, depending on orientation.
Okay, why the signs?
The signs allow for cancellation later. When you tally up all these counted paths between all the critical points, you build an algebraic structure. It's called a chain complex.
The chain complex, like a big list.
Think of it as a detailed map. The critical points are like cities, and the counted flow lines are like highways connecting them, each highway labeled with its count, plus 1 or -1. It's the complete record of the flow dynamics.
But if the space is huge, that map must be enormous, possibly infinite. How do you get something useful out of it?
Algebra comes to the rescue. You apply what are called boundary operators. Essentially, you look for paths that start and end in ways that form closed loops or boundaries in this algebraic map. Most paths end up canceling each other out, pairs of +1 and -1 paths.
So the noise cancels out.
Right. What's left over after all the cancellation represents the essential structure, the connections that don't cancel. These leftovers form the homology groups.
Homology groups, and these tell us about the topology.
Precisely. The size or rank of these homology groups gives us those Betty numbers we talked about earlier. Beta counts connected components, beta counts independent loops or holes, beta 2 counts voids, and so on.
So we went from a continuous, potentially infinite flow
Counted specific paths, used algebra to cancel out the redundant ones.
and ended up with a few key numbers, the Betty numbers, that describe the robust, unchanging shape of the system's dynamics. Like finding the number of holes in that donut, but for a flow.
You got it. It effectively quantizes the geometry. It compresses the continuous complexity into discrete, meaningful invariants.
Okay, that symplectic structure you mentioned, it helps guarantee these invariants are stable.
Yes, the symplectic structure provides the rigidity. Because the gradient flows we're interested in, like minimizing loss, often behave like Hamiltonian systems in physics, the symplectic framework ensures these topological counts, the Betty numbers, are well-defined and don't just change randomly if you slightly tweak the system.
It keeps the rules of the game consistent. Okay, but let's be practical. Solving complex PDEs to count these J-holomorphic curves in, say, a million-dimensional neural network space. That sounds computationally impossible.
It often is. For the full original FH, which is why people often use related theories or approximations, a really important one is Heegaard-Floer homology, or HFH.
A cousin theory. How is it more doable?
HFH came a bit later and was developed specifically for understanding 3- and 4-dimensional shapes, which are notoriously tricky in topology. The genius of HFH is that it manages to capture similar Floer-type information, but using purely combinatorial methods.
Combinatorial, meaning less calculus, more counting and graph theory.
Exactly. Instead of solving PDEs for curves, HFH involves things like looking at diagrams on surfaces, counting intersection points in a clever way. It's much more amenable to algorithms and actual computation.
So even if full FH is too hard for, say, a giant neural net, the existence of computable versions like HFH gives us confidence that the underlying idea of finding topological invariants is sound and potentially practical, maybe through other approximations.
That's right. It shows the core concepts can be translated into more tractable forms, which leads us directly into trying to apply these ideas to real computational problems.
Okay, let's make that leap. Segment 2. Using this topological machinery to certify computational hardness, we're talking about problems like SAT Boolean satisfiability. How can topology tell us if a SAT problem is truly difficult?
This is a fascinating application.
Yeah.
The big idea is to create a hardness certificate for things like cryptographic systems, one based not just on assuming factoring large numbers is hard, but on the measured topological complexity of the problem itself.
Okay, step 1 has to be, how do you turn a bunch of logical ANDs, ORs, and knots into a geometric shape?
It's quite clever. You take the SAT problem, the list of constraints, and you encode it as a specific type of geometric object, a Lagrangian submanifold inside a larger space called the cotangent bundle.
Whoa, okay. Lagrangian submanifold, cotangent bundle. Let's break that down.
Sure. Think of the basic space as all possible ways to assign true or false to your variables. That's like the ground floor. The cotangent bundle adds a sort of momentum dimension for each variable dimension. It's a space from physics, really, phase space.
Okay, so position and momentum, roughly.
By encoding the SAT constraints within this richer space, you define a smooth surface that's the Lagrangian submanifold. This surface represents all the variable assignments and their associated constraint forces that satisfy the problem.
So the discrete logic problem becomes a continuous surface in this special phase space. And finding a solution to the SAT problem is like finding a point on this surface.
Or, more accurately, understanding the shape of the surface tells you about the solutions. And the difficulty of finding a solution gets translated into topological obstructions on this surface.
Obstructions like loops, holes.
Exactly. Persistent cycles, essentially. Think of them as dead ends or pathways that an algorithm might get stuck exploring. The more complex the topology, the more loops and tangles, the harder the problem is likely to be. They use Morse theory, often as a proxy for full FH, to detect these.
So what are the specific numbers, the hardness barcode they use?
The main one is the first Betty number, beta 1. We met this before. Here, it counts the number of independent loops or cycles in the geometry derived from the constraints.
And more loops means more places for a solver algorithm to get lost.
Pretty much. For a graph representing the constraints, with no nodes, no edges, no interconnected parts, the formula is beta 1 wing in towns, met n plus CCO. Now, for hard problems, especially in crypto, they often use graphs called expanders.
Expanders, what's special about them?
They are sparse graphs, meaning not too many connections locally, but they are highly connected globally. It's hard to cut them into pieces. For these graphs, beta ANO tends to grow linearly with the average number of connections per variable, the degree delta.
So just by making each variable interact with a few more variables, increasing delta, you can dramatically increase the number of global loops. You create a tangled web.
Exactly. Delta controls local interaction, beta 1 measures the resulting global messiness. But there's another crucial invariant, persistence length.
Persistence length, what does that measure?
This is about topological rigidity. Beta now tells you how many loops there are right now. Beta tells you how stable those loops are if you start messing with the problem, like if an attacker tries adding or removing constraints to simplify it.
Ah, so it's resistance to attack or simplification.
If the cycles have a long persistence length, it means the fundamental tangled structure remains intact, even under significant changes. Tiane measures how long that topological shape survives.
Okay, so we have local connectivity delta, global loops beta 1, and rigidity p. How do they combine?
They propose an empirical hardness law. It's quite elegant. Hardness law is roughly proportional to delta times beta 1 times pi.
Hardness, connectivity, A loops x rigidity. Makes intuitive sense. Did they test this?
They did, using simulations. They'd set up hard SAT instances and then hit them with adaptive attacks, algorithms designed to break down the problem structure by adding or removing clauses strategically.
And what happened to the geometry, to beta and 100 and hundreds during this attack?
This was the striking part. Even under these adaptive attacks, the key topological invariants, beta and 100, often remained stubbornly fixed for long periods. The core topology was rigid and resisted the attack.
Okay, the geometry was tough. But did that actually predict how well a standard SAT solver would perform on the problem at those moments?
Yes. They used a standard, powerful solver called MiniSat to probe the problem during the simulation, and they found a direct correlation. When the geometry showed high rigidity, high and stable beta pen of $1, the MiniSat solver basically ground to a halt.
Ground to a halt how? Like, it crashed?
Not necessarily crashed. Its progress metrics flatlined. Things like the number of conflicts it resolved dropped to near zero. The number of times it had to restart its search was minimal, around 1. It wasn't making errors, it was just stuck.
So the algorithm was effectively trapped by the topological barriers, the loops measured by beta run 1, which were stabilized by the persistence of the war.
That's the interpretation. It suggests algorithms might fail not just due to time or memory, but because they literally get caught in the shape of the problem's solution space. It's a geometric trap.
Wow. And did they find this was universally true regardless of the specific type of logic used in the SAT problem?
That was another really interesting finding. They called it geometry-dominant hardness. They tried creating SAT problems using different underlying logical rules, like one based on XR constraints, another based on majority constraints.
So fundamentally different local computations.
Right. But if the overall graph structure, like using the same expander graph, was kept the same, the resulting floor barcodes, the measured beta velotter and pedal values, were identical.
So the specific logic at each step mattered less than the large-scale pattern of connections, the topology of the constraint graph.
Exactly. It suggests the high-level geometry, the network shape, is the primary driver of this kind of hardness, not the fine-grained details of the constraints themselves.
Which really bolsters the idea of using these topological invariants as a kind of universal post-quantum hardness certificate. It's based on shape, not just number theory assumptions.
Precisely. It's about the provable persistence of these topological knots in the problem space.
Okay, this is fascinating. Topology predicts the hardness of statting problems, like SAT. Now, let's pivot. Can we use the exact same ideas, critical points, flows, Betty numbers, for the messy dynamic process of training an AI? Segment 3, the secret geometry of AI.
It's a surprisingly natural transition, because training a neural network, using gradient descent or its variance, is fundamentally about navigating a landscape, the loss landscape.
Right, minimizing the error by rolling downhill.
And that loss landscape, defined over potentially billions of weight parameters, that is our flow action functional from segment 1. The process is a gradient flow on a high-dimensional manifold.
Okay, but again, the scale is immense, billions of dimensions. Full flow or homology is outright.
Absolutely impossible computationally. So just like with the hardness work, researchers use proxies. Often it's a Morse-Floer hybrid proxy. It uses the classical tools of Morse theory combined with the algebraic machinery of Floer, focusing particularly on the lower-order homology groups.
And which group turns out to be key here?
For understanding basic training dynamics, the first homology group, H$1, seems really important. Remember, H$1 measures loops or cycles. H$1 means no persistent loops, basically a connected space. H1 or higher means there are topological barriers.
So H$1 is our main indicator again. And the amazing claim is that the choice of activation function in the neural network dictates this H1 value.
That's the core finding of the research we're looking at. The activation function, that simple nonlinear step inside each neuron, fundamentally shapes the geometry of the entire loss landscape.
Let's compare the big two then. Start with ReLU rectified linear unit. Famous for being simple and effective, but it has that sharp corner, that kink at 0.
That kink is everything, topologically speaking. Because the function's derivative jumps discontinuously at 0, it creates sharp edges and corners in the loss landscape. The analysis using the Morse-Floer proxy shows this leads to non-trivial homology, specifically H$11.
So the ReLU kink creates loops, topological barriers, in the loss landscape. What about the starting point of training when weights are near 0? What did the analysis show about the origin?
It showed the origin for ReLU tends to be a flat region, with a Hessian index of 0. An index 0 critical point means there's no negative curvature initially to push the optimizer strongly away from the start.
So you start flat, and the landscape around you is potentially filled with an H1 to 9-1 loops or traps. Sounds not ideal.
It suggests a risk of getting stuck early or wandering into regions you can't easily escape. Now contrast that with smoother activations like a GELU variant they studied. GELU avoids that sharp kink.
GELU is smooth everywhere. Gaussian or linear unit?
Exactly. Because it's smooth, its derivative is continuous. And the topological analysis, it found trivial homology, H1 $39, no persistent loops. The landscape is fundamentally connected.
A completely different topology just by smoothing out that one activation function. What about the origin for GELU?
Also different. The analysis showed the origin was typically a balanced saddle point with index 6.
Index 6. Okay, what does that mean practically? Is that better than index 0?
Much better for optimization.
Yeah.
A saddle point means there's negative curvature in some directions.
Yeah.
The index tells you how many. And positive curvature in others. An index 6 saddle provides enough downhill push in multiple directions to get the optimization process started efficiently and stably, guiding it away from the origin and into the broader landscape.
So topologically, we have ReLU, flat start, H1 loops, traps, and GELU, saddle start, H1 are connected. That's the prediction from the geometry. Did it hold up in actual training experiments?
It did remarkably well. They trained a standard deep MLP network on the CFAR10 image dataset, comparing ReLU and the GELU variant.
What were the results for GELU, the H1 network?
The GELU network reached a training accuracy of 70.65%. And interestingly, it did so while using parameters with a larger overall magnitude, a higher norm, 138.69.
What does the higher norm suggest?
It suggests that because the H1 landscape was smooth and connected, the optimizer was able to explore much further, finding solutions that utilize the network's capacity more fully. It wasn't confined.
Okay, and what about the ReLU network, the one predicted to have 1-1 topological barriers?
The ReLU network only reached 63.52% training accuracy. That's a full 7% lower than GELU on the same task, same architecture.
Wow, 7% is a big difference in ML benchmarks.
It really is. And the interpretation lines up perfectly with the topology. The H11 cycles acted as predicted. They created barriers or traps that prevented the optimizer from finding the better solutions that GELU could access. It likely led to getting stuck in poorer local minima or suffering from mode collapse.
This is pretty revolutionary for how we might think about designing networks. Instead of just trying activations and seeing what works, we could potentially predict performance based on the topology they induce.
That's the implication. The topology, specifically that H11 invariant, acts as a predictor for training dynamics. Smooth activations that ensure H1 and provide a helpful starting geometry, like that index 6 saddle.
They create what the researchers called the Goldilocks geometry.
Exactly. Just the right shape, smooth enough for optimization to flow well, but still complex enough, thanks to the network depth, to be expressive and learn complex patterns. It balances trainability and capacity.
So the sharp kinks that give ReLU some of its theoretical power also create these topological hurdles, these H1 BL1 cycles, that hinder the actual gradient descent process.
It's a trade-off. The smoothness of GLU avoids the hurdles, allowing the optimizer to follow the least action path more effectively, like we discussed with Floor homology's origins.
Which brings us neatly to the conclusion, the grand synthesis. We're tying together quantum physics, computational hardness, and AI training through this one geometric lens.
It feels like a really deep connection. That H1 versus H1 binary distinction isn't just abstract math, it's like defining two different physical regimes for the computation.
What's the physical analogy?
You can think of the H1 landscape from GLU as operating under classical smooth mechanics. Gradient descent follows predictable, smooth paths geodesics, essentially towards a minimum. It's stable, reliable flow.
Okay, nice and classical. What about H1?
The H1 topology, seen in ReLU and those hard SAT problems, introduces something more like quantum-like barriers or fragility. The discontinuities act like little defects or potential wells, creating local traps, unpredictable jumps, and the risk of getting stuck in cycles. The flow is less smooth, more prone to getting snagged.
So smooth activation functions allow classical optimization, while sharp ones introduce quantum-like complications. That's a powerful image.
And it's amazing that this mathematical framework, Floor homology, developed to understand instantons in fundamental physics, now provides this precise language to describe why one activation function trains better than another.
And the connections go even further, right? Floor homology isn't isolated. It plugs into other big areas of math and physics.
Absolutely. Its origins in gauge theory mean it feeds directly into things like topological quantum field theories, TQFTs, theories where the only relevant properties are topological invariants.
And you mentioned knots earlier.
Yes. FH has deep connections to knot theory, the study of tangled loops in space. This is incredibly relevant today because it inspires ideas in quantum computing.
How does knot theory relate to quantum computers?
One of the holy grails is building topological qubits. The idea is to encode quantum information not in fragile local states, but in the global topology of some physical system, like the braiding patterns of exotic particles. These topological states, like complex knots, would be intrinsically robust against local errors and noise.
Wow, so the same math that counts loops in a loss landscape might help build error-proof quantum memory.
That's the dream. We're moving from guesswork towards geometry-informed design.
It really seems like the deep structure of problems, whether in security or AI, is fundamentally geometric.
It really does. The future might be less about counting components and more about understanding the shape of possibility itself.